Hello again. This is video lecture 29.4, and we're studying sections 4 and 5 in chapter 29. And section 4 is going to talk about calculating magnetic fields for two rather particular current distributions. One is what's called a solenoid, and the other is called a toroid. We're going to start with a solenoid. We're going to use Ampere's law to find the magnetic field inside an idealized solenoid. So the first thing we have to explain is what a solenoid is. And I have here in the lower left a photograph of what a physicist would typically have in mind when they say the word solenoid. And all it is a cylindrical frame that's usually considerably longer than it is wide, and that they've taken conducting wire and they've very tightly packed the windings of the wire around and around and around from one end to the other. Okay? And then we're going to hook it up to a battery or a power supply and run current through that wire, making magnetic field. This device is called a solenoid. Note that it looks somewhat like the coils you were using in lab in this most recent experiment. But the difference here is that the coils in lab were not as long relative to their width. In fact, they were almost wider than they were long. A solenoid tends to be considerably longer than it is wide, so that you get a pretty long, kind of like a tunnel going down. And the wires are wrapped around, very tightly spaced, just one after the other. Usually sometimes in this case, in just one layer, going all the way down. This is the device we want to calculate the magnetic field for. Now, the picture in the middle is very loose representation of some of what's going on when you have current going through these windings or turns of the solenoid. And it's kind of difficult to understand what this picture is showing. This picture is showing five different turns or windings of wire, which are basically, when you look at them, just circles going around. And all you're seeing here is a kind of a cross-section where you're seeing the back half of these 5 circles. And with these 5 circles, the current is going, for each circle, into the screen at the bottom, upward on the circular arc at the back, I should use an X, and then out of the screen at the top, and then going down at the front. So just imagine you got current going around in a circle. Now what you really got is it goes around in a circle, and then it goes to the next circle right beside it, and then the next circle right beside it. But they're so closely spaced, you can just think of them as independent circles. And then you see some magnetic field lines that are produced by the current going around in each of these windings. And let's look at the kind of behavior of those magnetic field lines. Remember, where the magnetic field lines are more tightly spaced, the field is stronger. And the arrows on the magnetic field lines give you the direction of the magnetic field. So the main thing to note, even with just these 5 turns, this is far from being a real solenoid, that the magnetic field lines are pretty tightly spaced in the region that you would call the inside of the solenoid. That means the field is strong. The field points to the right in this case, in that region, and it's strong. And the spacing is more or less uniform. So the field is more or less uniform inside there. Now in the outside region, outside the windings, you don't have that many magnetic field lines spaced closely together, so the field is weak outside. Okay, so the things we observed just from the field line drawing. The magnetic field is weak outside the solenoid. The magnetic field is strong and nearly uniform in the interior. And the direction of those field lines and of the field is given by yet another variation on the right-hand rule. Just a kind of a shortcut way to figure out the direction. You imagine taking your right hand and grabbing hold of the solenoid and wrapping your fingers around it in the direction the current's going around in the windings. And then your thumb points in the direction of the magnetic field. So for these windings, all right, if I imagine the windings are in front of me, then the current's going away from me at the bottom, up at the back of the circles, towards me at the top, and down at the front. So I curl my fingers that way. My thumb points to my right. And that's what's telling me that the magnetic field in the interior region points to the right for this solenoid. Now we're going to study what's called an idealized solenoid. And here's the next schematic of that. It's another cross-sectional view. And here what we're idealizing the solenoid to be is a whole bunch of circular turns, one beside the other, going down the line. And each turn, and we're seeing just the back half of each turn in this cross-sectional view. In each turn, the current goes away from us into the screen at the bottom, up the circular arc at the back, out of the screen towards us at the top, and then down at the circle in the front. And you've got a whole bunch of these turns, these windings, these circles, and they're all stacked side by side, moving down the solenoid. And each winding carries the same current, I. In that idealized solenoid, where the turns of the windings are butted up right up against each other with no gaps, the magnetic field inside is completely uniform, and by that special right-hand rule to the right, and the magnetic field outside is zero. Okay? All right, so let's highlight that for the idealized solenoid. The turns are very closely spaced. The magnetic field is uniform in the interior of the solenoid. If you think of it as a tunnel, when you're inside the tunnel, the magnetic field is zero outside. And in addition to the current I going around each winding, I need to know one other property of the solenoid. It's denoted by the symbol little n. It's the number of turns per unit length, per meter. And turns means windings or circles of wire. Okay? So if I think of measuring distance going to the right, that way, it's the number of turns per meter of length going rightward. The number of turns per unit length, with unit of 1 over meter. All right, so with all that in mind, we can use Ampere's law to calculate the magnetic field B in that interior region. And we choose an Amperian loop that follows B, at least for part of the loop, and along the rest of the loop, there's no contribution to the magnetic circulation. And so the Amperian loop that we're going to choose is a rectangle in the plane of the screen of length h. And that's shown there in that kind of orange rectangle. The four corners of the Amperian loop are labeled, little a, little b, little c, little d. And the arrows show which way we're going to do the magnetic circulation integral, counterclockwise. And we do that specifically so that along that edge right there, we're following B. All right, so we start, if we're going to apply Ampere's law, by writing down a symbolic expression for the magnetic circulation around that Amperian loop. And since it's a rectangle and it's got four sides, I find it convenient to break this up into four separate integrals. One integral of b dot ds along each side. So I'll have to integrate from a to b along the bottom side of the rectangle. And then I'll have to integrate b dot ds from b to c along the right side. And then I'll have to integrate b dot ds from point C to point D along the top side. And then I'll have to integrate b dot ds from D back to A along the left side. And then I will have done one complete loop. All right. First, let's look at that integral, b dot ds from B to C. So along here. Okay? I contend that the integral of b dot ds is 0 along that side. Let's talk about why. Well, if I'm integrating in the direction shown, then any little ds that I have to deal with, like right there, is in that direction, but I've got to do B dot ds. So when I'm down here in the interior region of the solenoid, the B is to the right, remember? And that B and that ds are perpendicular. And B dot ds then is 0. That's if I'm on that side and I'm inside the solenoid. What if I'm along that same side but outside the solenoid? Like up here. There's a little ds in the exterior region. Well, there is no B there, right? B equals 0 outside. So for different reasons, I come to the conclusion that along the length BC, there is no B dot ds. All right, now let's do the integral from C to D. You see what I'm going to get for that integral of B dot ds? Did you say 0 again? And why? Because alongside CD, there's no B to do a B dot ds, right? All right, and then let's do the integral of B dot ds from D to A. So now we're talking about that way. I contend again that the integral of B dot ds is 0. Do you see why? Well, if I'm outside the solenoid, there's no B at all. And if I'm inside the solenoid, there is a B, but it's perpendicular to ds. So notice then, the only contribution I'm going to get to the circulation is when I integrate B dot ds along the segment from A to B. So now we focus on that. So now I just integrate from point A to point B. So now all this other stuff can go. And now I imagine a little step along here, maybe right there. There's the ds. But the B that's the same direction as the B, isn't it? So this would be then the integral from little a to little b of magnitude B, magnitude ds, cosine 0 degrees. Cosine of 0 degrees is +1. And the magnetic field is uniform when you're inside. So guess what? I get to bring the B magnitude out front. Now I'm just integrating from point A to point B, all the little step sizes ds, but that's just going to be the total distance from little a to little b, right? Just from A to B. But that's that length that we're calling h. So I just have magnitude of B times h. And that's my expression for the magnetic circulation. And so that goes on the left side of Ampere's law. So here's Ampere's law written down. And when I put that in on the left side, there I have magnitude of B times h. Next, I need the right-hand side of Ampere's law, which is mu0 times I enclosed. I need the total current that is enclosed or encircled by my Amperian loop. So I have to imagine a surface inside the Amperian loop. Let me shade it. It's this rectangular area, right? So you have to think of that as kind of like a surface right there. And I need to add up all the current that pierces that area, all of it. By the way, since I opted to do my Amperian loop circulation integral counterclockwise, when I curl my fingers counterclockwise around the loop, my thumb points up. An upward current is a positive direction for I enclosed. But now what we've got to be able to visualize is, where is current piercing that surface I shaded in yellow? Can you see where it is? We have to be able to visualize this. Right there. Do you see all those blue dots? That represents current in each winding or turn coming towards you. Straight towards you, out of the screen. And that's then piercing that yellow surface. And out of the screen, so it's a positive contribution to I enclosed. The only question is, how much total current is it? Remember, the current is I through each winding. So I'll take I times the number of windings that is. Now the drawing is schematic, so I can't just sit there and count those windings. I have to use this other property, I'm told, that there are little n turns per unit length. So if their little n turns per unit length this way, then all I need to know is how long the Amperian loop is this way. Well, that length is h. So the total number of windings inside the loop is little n times h. And I multiply that by the current I in each winding, and so little n times h times I is the total current enclosed. Multiply all that by mu 0, and I have Ampere's law. Notice there's an h on both sides. I can divide it out. So that choice of how long that Amperian loop was does not determine the answer for B. And there's the pretty famous answer for the magnitude of the magnetic field in the interior region of a solenoid. Mu 0 times the number of turns per unit length times the current going around each turn. And it's nice and uniform magnetic field inside. And the direction is given by that right-hand rule. And we've used Ampere's law again. In this case, to find the magnetic field of a somewhat important device, a solenoid. Why important? Because it's a way to get a uniform magnetic field. And if you'd like to be doing an experiment on a sample that's immersed in a uniform magnetic field, you want to have a solenoid. And put big enough that you can insert your sample into it. Okay, so we'll use that result quite a bit for the magnetic field of a solenoid. Here's a little mini practice. We'll just do this together right now. Magnetic field of a solenoid. This figure, very simple, very schematic, indicates the directions of the current in one turn of a long, tightly packed solenoid that is horizontal. So you can think of the solenoid itself being something like that. Okay? With windings one after the other. And you're seeing one of those windings there. The question is, what is the direction of the magnetic field inside the solenoid? Rightward or leftward? I'd like you to try that for yourself. Pause the video so you can think about it. Come back when you're ready. All right, so you basically want to use the shortcut right-hand rule to get the direction of B. All you got to do is imagine that there's the cylindrical solenoid. You're going to reach in with your right hand and grab a hold of that cylinder with your fingers wrapping around it in the direction the current is flowing. And so as I imagine this cylinder right in front of me, I'm going to reach in, and at the bottom, the current is going away from me into the screen. It's going up at the back. I said that backwards. I beg your pardon. At the bottom, let me say that again. The current is coming out of the screen towards me. Up at the front, away from me into the screen at the top, and down at the back. Okay? All right, so how do I have to grab hold of that cylinder with my fingers curling around the way the current's going? Right? Away from me at the top, towards me at the bottom. I have to go around this way, and my thumb points to my left. So that means in this interior region, I have a nice uniform field everywhere in here, in the interior region of this solenoid, and it points to the left. Note that there's only two ways that you could have current in a solenoid drawn like this. Either with the current going like that, away from you at the top and toward you at the bottom, or the opposite, toward you at the top and away from you at the bottom. And if that were the case, the magnetic field in the interior would be pointing to the right. So you have to be able to use that specialized right-hand rule, okay, to get the direction of B. All right, so now we've studied a device called a solenoid. And now we're going to use it to make another device. It's called a toroid, or a torus. And a toroid, an idealized one, is when you take an idealized solenoid, so you think of it as being a long cylinder, much longer than it is wide, with very closely spaced windings, one after the other, all the way down. But you imagine that the cylindrical frame it's on is flexible. And then you take the two ends and you bend them around in a circle and connect them together. And you make what is, in essence, a donut shape. And here's a representation of it, kind of from an angle. Okay? Think of a donut shape. Okay? With the current, with the windings going around and around and around like this. Okay? And we pass current I in these windings. Each winding. And the way we're doing it with this toroid is that the current's coming up in the front, kind of away from us at the top, down at the back, and toward us at the bottom in this top view. Now the second picture underneath here is a slightly different perspective. Now imagine looking down on the toroid from above and take a horizontal cross-sectional slice through the middle of it. And pretend you could peel the top half off so that you see just the bottom half. It looks like this second picture, with all those windings of wire now looking kind of like little mini circles. And in each one of those outer windings, the current is going away from us, which means downward, the current I, all the way around. And each one of those windings on the interior circumference, the current's coming up towards us. I'm sorry, my eyes are bad. I beg your pardon. I'm having a hard time seeing it. I said it backwards. For each of the windings on the outside, like there and there and there, the current is going up that outside wall of the toroid coming towards us. And for all the windings on the inside circumference, the current is going downward away from us, all the way around. Okay? All right. What's the magnetic field created by the current going around all those windings when you've taken the solenoid and wrapped it around to make a donut? To be clear, hopefully, the whole of the donut's in here. There's no actual stuff there. It's the whole. The interior of the toroid is here. In what was the interior of this solenoid, in the tunnel region inside the solenoid, before we wrapped it around and put the ends together. That's where the magnetic field is, in the tunnel part. Okay? And from kind of the specialized right-hand rule, if I wrap my hand around the toroid, the right hand, the way the current's flowing, and look at the way my thumb points, that tells me the way the current's, the magnetic field's going. And what you end up with is circular geometry, is that the magnetic field lines are circles directed clockwise. Okay? That's the magnetic field, B. Okay? The magnetic field circulates clockwise around the interior of the toroid, and the field is zero when you're not in the interior of the toroid. So that would be in this region, which, if I think of this as a donut, would be in the whole of the donut, and of course in the outer area. If I think of this as a donut, the magnetic field is only in the place where the dough is. And in this case, it circulates clockwise. So we're going to choose an Amperian loop. That is a circle. And we've chosen one here. It's drawn kind of in orange. And we're going to integrate around it for the circulation integral clockwise. In other words, follow B. And the circle, the Amperian loop, has a radius r. All right, so when you write down the formula for the magnetic circulation, you can go through the steps. Because the magnetic field just circulates and is clockwise and tangent to the circle, and will have the same magnitude all the way around, you get B times the circumference of that circle, 2 pi r. That's the left side of Ampere's law. Then you need the right side. Mu0 times I enclosed. So now what I need is all the current that is enclosed by the Amperian loop and pierces, therefore, the surface inside the Amperian loop. So let me shade all that surface in. That's the surface inside the Ampérian loop. I've got to be able to visualize where the piercing of that surface is. You see where it is? It's where all these windings on the interior circumference of the toroid are going downward, with the current going inward, all the way around. Okay? And every winding carries the same current, I. And there are capital N windings total. Be careful, not little n, like for a solenoid. Little n was number of turns per unit length. This is just big N, and it's just the grand total number of windings of the wire around the toroid. Well, every single winding pierces the interior of the Ampérian loop here. I'll just draw it in like that. On that interior circumference going inward. So the I enclosed is just capital N times I. Total number of windings times the current in each winding. And then all we do is take that formula and solve for B. It'll be the magnitude of B, and you get mu 0 capital N I over 2 pi R. R is downstairs. So the magnetic field does depend on how far you are, distance, from the very center of the hole. And the larger distance, the smaller the field. So it's a non-uniform field now. You started with a uniform field in a solenoid, and then by wrapping it around and connecting the two ends, changing the geometry, you've created a non-uniform field. That doesn't go in a straight line, but circulates. Okay? So that's another very useful result that we will use. The magnetic field in the body of a toroid. Okay, there's one more section to talk about. Chapter 29, section 5. And now we're going to talk about a current carrying loop as a magnetic dipole, and calculating the magnetic field on the central axis of a current carrying loop. All right, so here's what we're imagining now. The picture here shows just a circular loop of wire. Circle. Okay? But, and that loop carries current I. And that circle has a radius big R. But we will take wire for this loop and we'll wrap it around multiple times. But just, it's still flat. Okay? So we'll have capital N windings, or turns, with current I in each turn. The loop is a circle with radius big R and therefore has an area inside it of pi big R squared. What magnetic field does that create? And interestingly enough, such a thing, we call it a coil, acts like it's kind of the simplest example of what we call a magnetic dipole, which we talked about briefly in chapter 28. It behaves, in fact, much like a simple bar magnet, with the magnetic dipole moment, mu, of N, number of windings, times current, times the interior area. And the direction of that magnetic dipole moment vector, yet another right-hand rule, wrap your fingers around the loop in the direction of the current, your thumb points in the direction of the magnetic dipole moment, it's that mu vector there pointing up. And this loop, the actual physical thing, is the loop of current, oriented like so, acts like a bar magnet, with its north and south poles oriented up and down, north on top, south on the bottom, creating magnetic field lines like you see. We are going to calculate the magnetic field at any point on the central perpendicular axis of the loop. We can't use Ampere's law because there's not enough symmetry in this current distribution to enable us to choose an Amperian loop that will make it easy to write down the integral of B dot ds formula. We have to use brute force, which is called the Biot-Savart law, the first method we learned in chapter 29 for calculating magnetic field. All right, so our task here is to use the Biot-Savart law to find the magnetic field at a point P on the central axis. So let me show you this picture that's below. Let me expand it a bit so maybe you can see it better. There's the circular loop. carrying current I, having radius big R. The z-axis I chose to be the central perpendicular axis, perpendicular to the plane of the loop, going through the center, with plus z going up. And there's this point P right there that we've just picked right on the z-axis at a coordinate z from the center. What's the magnetic field? Right there at point P. I'm going to tell you the answer, and then I'll show you the proof of it. Okay? At that point P. Here's the answer. B, magnitude. The direction is straight up the z-axis. You can see its directions drawn right there. Its magnitude is given by this formula. B magnitude. Mu 0, I, current going around, N, number of windings of wire, big R squared, radius squared, over 2 times R squared plus Z squared to the 3/2. Now we can take capital N times I times A, which is capital N times I times pi R squared, and that's the magnitude of the magnetic dipole moment of the loop. And if we do that, we can write the formula for B magnitude this way. Mu 0 over 2 pi, mu magnitude, magnetic dipole moment vector magnitude, over R squared plus Z squared quantity to the 3/2. That's what I'm going to derive. But anytime we need to find the magnetic field on the central perpendicular axis of a loop with n windings, we can go straight to this formula. Okay? We don't have to rederive it. Once we do, we can just use this result. I will, however, tell you a special case of this answer. If the point P is very far out on the z-axis, so not like what you see here, but much farther out, way up here somewhere. Okay? How does this formula for B simplify? So I'm looking at the special case where Z is much, much greater than R. Well, then all you do in the R squared plus Z squared is drop the R squared. It's small compared to the Z squared. And then I have Z squared to the 3/2, which is Z cubed. And the B magnitude formula then simplifies to that. Mu 0, mu magnitude over 2 pi Z cubed. It goes like 1 over the Z distance from the center, cubed, not squared, cubed. If that seems odd, I'll just point out, we've seen that behavior before. In the electric case, when we had an electric dipole with the dipole moment P along the z-axis, and we're at a point P that's very far away from the center of the dipole, the electric field is then P magnitude over 2 pi epsilon 0 Z cubed. So the magnetic field far away from either an electric dipole or a magnetic dipole goes like 1 over distance cubed. Okay, we're going to end the video by going through a kind of an outline of the proof of this result up here. For the magnitude of the magnetic field on the central perpendicular axis. So here's a picture, side view of the loop. Loop looks like a line, but you're looking at a loop from the side. And there's a little tiny piece of the loop, length ds, way over on the left side, facing us with the current coming out of the screen towards us. That's what this symbol means. And that's a little current element of length ds. And there's the point P up on the z-axis. And so I also need the distance r from that point P to the little current element, ds, and the unit vector r hat that points from the current element to point P. Because I'm going to use the Biot-Savart law and get dB, okay? The contribution to the magnetic field at point P from that one little element, mu 0 I over 4 pi r squared downstairs, ds cross r hat upstairs. And this diagram shows the dB vector. Now, because the direction of dB is determined by ds cross r hat, dB has to be perpendicular to both ds and r hat. And it's kind of hard to visualize, and given by the right-hand rule, what you get when you do ds cross r hat, but it's right here. Okay? That's the dB. And it is, in fact, perpendicular to that line labeled r. And in the direction from the right-hand rule of ds cross r hat. And we have broken up that dB, resolved it into a component perpendicular to the z-axis. They label that dB perpendicular. And a component parallel to the z-axis, which they label dB parallel. And they've identified an angle alpha here, which is also this angle down here, which is going to be useful. Okay? All right, now that's just the dB at point P from that one little element of the loop, but I've got a whole bunch of them because I have to go all the way around the loop once. It's convenient then to consider the diametrically opposed element exactly across the diameter on the other side of the loop, which would have the current going away from us into the screen, ds, and the corresponding r, distance. The point P would be that. And the corresponding r hat would be that. And think about the dB from that little element. And what I contend is that it has to be perpendicular to ds and r hat, this ds, which is pointing into the screen, and this r hat, and in the direction of the right-hand rule for ds cross r hat. And that ends up being just like that. I mean, I hope it's clear that there will be its perpendicular component, dB perpendicular, and there will be its parallel component, dB parallel. And these two perpendicular components of those two opposing elements cancel. But the parallel components add. So all I really have to keep track of is the dB parallel components, which would be magnitude dB cosine alpha. And that's what I have to add up to get the total magnetic field at point P. So the B parallel total is the sum of all the dB parallels. So I have to figure out what to put for that. Well, that's the sum of dB magnitude cosine alpha. Let's write out what we know about all those things. dB magnitude. That comes from this formula right here. That will be mu 0 I over 4 pi r squared downstairs, and then magnitude of ds cross r hat. That'll be magnitude ds, magnitude r hat, 1, right? Sine, it's cross, sine of the angle between ds and r hat. Well, ds down there in the lower left is coming straight out of the screen towards you, and r hat is in the plane of the screen. You might want to do 2 pens or something to visualize it, and you can even look at them, and you can see that, in fact, the angle between them is 90 degrees. Sine of 90 degrees, the sine of 90 degrees is +1. So this magnitude is written mu 0 I ds over 4 pi r squared. Now, what can I say about that factor of cosine alpha? Well, let's use this right triangle down here where the alpha is in the lower left. Cosine alpha then is adjacent over hypotenuse. That would just be big R over little r. So let's put all those things together in the expression for B parallel. That's the integral of mu 0 I big R over 4 pi little r cubed ds. All right, I put in cosine alpha as big R over little r. I'll pull the constants out front. I need to know, as I circulate around this loop exactly once, which of these quantities stays the same. It turns out everything stays the same, so you bring out everything except the ds. You can never bring the infinitesimal out front. Never, never, never. Everything's the same. Every loop is the same distance big R from the center of the loop and the same distance little r to point P. And so this means just add up all the little steps around once. Well, that's the circumference, isn't it? So what's the expression for B parallel? Mu 0 I r. The circumference is 2 pi big R over 4 pi little r cubed. Well, let's see. 2 pi and 4 pi do some canceling. And note from the Pythagorean theorem that little r is the square root of big R squared plus z squared. So this expression is mu 0 I big R squared over 2 times big R squared plus z squared to the 3/2. And that is that formula right there. Okay? So we can use that. Now that's for one loop, right? For one loop. I should add that. For one loop of wire. Sometimes you'll see, even though it's a flat circular shape, they'll say that the wire goes around n times. So to get the total, just multiply all this by big N. Okay, the last thing I'm going to leave you with is a class engagement for Blackboard. Okay, the magnetic field on the axis of a current-carrying loop, what I was just talking about. Let's apply that result to a somewhat more complicated scenario. This figure here shows 4 arrangements of circular loops. And the loops either have a radius of big R or 2 times big R. They're all centered on a vertical axis that's perpendicular to the loops. And they're all carrying identical currents in the directions indicated by those arrows. Our task is to rank these arrangements according to the magnitude of the net magnetic field at that dot. See where the dot is? The dot is exactly midway between the loops on the central axis. And do this ranking, largest to smallest. To help you do the ranking, call the current I in each. The radii are either R or 2R. If that's a smaller loop, it must be R. If it's a bigger loop, it must be 2R. And let's say the distance along the perpendicular axis from the center of each loop to the dot is big D. You'll need that to help you organize your thoughts, because you're going to have to take the result we just derived and you're going to have to figure out B net at that center point between them in each case. You got to figure it out using the formula we just derived to find the B net, and then you can rank them biggest to smallest. That's your practice. That's all for this video, and then we'll have a class video where we will apply these ideas. And that's all for now.